This video is an introduction to how capacitors behave in circuits. We're going to look at the behavior of a capacitor at two specific times. When we first connect a circuit and the capacitor starts charging, and then after a very long time when the capacitor has reached its full charge. Obviously the time between those is interesting and we'll look at it qualitatively, but a mathematical treatment of those times is not part of this course. What happens when you first plug in this circuit? Well, I think you can see there's two paths for current. There's through this loop, and then there's through this loop. But can current really flow through a capacitor? There's a gap between the plates. This is either air or some dielectric, and charge can't flow across it. But when you first plug the capacitor in, the battery is going to be putting electrons on this plate, giving it a negative charge. And it's going to be ripping electrons away from this plate, giving it a positive charge. So even though current can't flow across the plate, we have negative electrons going to here. We have electrons going this way as they're being ripped away from this plate. So at first, it's almost like this is a regular wire, like it's got no resistance at all. That doesn't last long though. As the capacitor starts to charge, there's more and more electrons here, there's less and less electrons here. It becomes harder to add electrons and take them away as it gets more charged. And as a lot of time passes, we get to the point where the battery can't put any more here, and it can't take any more away from here. At that point, the capacitor is charged, it's storing energy. But another thing has happened. The flow of charges in and out has stopped. So after a very long time, we expect the capacitor to act like an open switch. Charge can't flow through it. In which case, the charge would only be able to flow through this loop here. So in this video, we're going to examine capacitors in these states. We're going to watch what happens to the potential difference across them and other elements in the circuit. And we're going to start by looking at a case where we just have a resistor and a capacitor in series with each other. In this circuit, we can charge capacitor C1 by hooking it up across a power supply. Resistor R1 and C1 are going to be in series with each other. And we can charge it by closing this switch and leaving that one open. And then to discharge it, we open this one and close that one. So let's take a look at this idea of a capacitor acting as a regular wire when it's first connected in a circuit and acting as an open switch later. I'm about to set up a circuit here where we can charge the capacitor by closing this switch. We can discharge it by opening it and closing that one. So look at what happens as we charge and discharge this capacitor. And we can monitor what's going on in the circuit by looking at the potential difference across the resistor. With this voltmeter here. And we can look at the potential difference across the capacitor with this voltmeter here. So in order to set this up, what we'll do first is it says the positive of the power supply, which is 5 volts, is connected first to a switch. And I believe that's what I've got here. And then that switch is connected to a resistor. This is a 51K resistor. I've chosen this capacitor and this resistor because they charge and discharge in a nice kind of pretty amount of time. It's not too long, not too short. So we can see what's happening. We'll look at how different combinations work a little bit later in the video. This resistor is then connected to the capacitor. This kind of capacitor is known as an electrolytic capacitor. There's a negative arrow pointing this way, so this side's the positive side. Electrolytic capacitors don't work right if you hook them up wrong. In fact, they often explode. The capacitor is connected back to the negative of the power supply. And nothing's happening because our switch is open. Now, there's some other connections too. The capacitor also appears to be connected to the negative of this switch, which we can use to discharge it later. And the positive of that switch was connected back here in front of this resistor. So we're all nearly hooked up. The only thing left to do is make sure our meters are set right. And we'll connect the capacitor meter here. And we'll connect the resistor meter here. Don't worry if these show a negative sign, it just means the meter is hooked up opposite to what it was expected to. All right, so what should we see as our potential difference across the meters when I first turn this on? Well, at first, if a capacitor really acts as a bare wire when it's discharged, what we should see at first is that this isn't here, and all 5 volts should drop across the resistor. So we expect this meter to say about 5, and that meter to say close to 0. As this charges, as it builds a bigger potential difference across it, we expect this meter to grow. And that's going to act less and less like a wire and more like an open switch. That's going to mean current should drop. And since this voltage drop equals IR, we should expect the potential across the resistor to decrease. So let's start charging and see if that's what happens. So let's close this switch right here, and we'll see if that's what happens. So I don't know if you saw that, but it started out relatively high across the resistor and then dropped to 0 as current stopped to flow. Voltage drop depends on both current and resistance, and if we got no current, that means we're not dropping voltage across here. The capacitor is now totally charged, and it's got our 5 volts. So we're now acting as an open switch. There's not current flowing in the circuit. We'll disconnect the power supply, and we'll discharge the capacitor through this switch. And we can see briefly as it's discharging, the potential difference across here shot up as the current increased, but then it disappeared as we essentially lost all the stored charge. Before we do anything else, I want to kind of look at what effects the resistance and capacitance have on how long it takes to charge and discharge the capacitor. Well, we've got 2 different resistors that differ by a resistance by a factor of 10, and 2 different capacitors that differ by a capacitance of a factor of 100. We're going to see both of these variables matter. All right, so this is charging the capacitor. I'm going to throw this switch, and we're going to get an idea with the bigger capacitor and the bigger resistor. We'll get an idea of the rate at which this seems to happen. Here we go. This is not going to be a constant rate. As we start to get more and more charged, it's going to start to slow down. I don't know what that meter is angry about. So if we left it for a very long time, we'd eventually approach 5 volts. We'll see how much patience I have to do that. So let's discharge this capacitor. Let's disconnect the power supply. It'll start to drain slowly as it discharges through the meter, but it will discharge much quicker if I close that switch. So you can see it draining off. All right, here is charging the circuit with the big capacitor and the small resistor. So we can see it starts to charge much quicker. It does slow down towards the end like it did for the other one, but it got to that value much quicker. So we'll disconnect power and we'll discharge it. We can see with the smaller resistance it discharges much quicker. Okay, so let's now use the smaller capacitor. This is a ceramic disc one, not an electrolytic, so it doesn't require paying as much attention to positive and negative. This is going to be charging with the small resistor and the small capacitor. We can see it charged nearly instantly. So smaller values for resistance and capacitance seem to make the capacitor charge quicker. Disconnect. And that was actually able to discharge through the meter before I could even get the other switch closed. Let's repeat the charging. Let's see if I can get the other switch closed quick. Yeah, that was almost instantaneous. So don't forget the meter is in parallel with the capacitor. So this is another possibility for current to discharge through. So apparently having the small values for capacitance and resistance means it charges and discharges very quickly. And we might as well collect all possible combos. So now we'll do the small capacitor and the big resistor. So I expect, since having big values of resistance and capacitance made it take longer, having small values of both made it take shorter. Since I've upped the resistance, I expect this one to be more than the one where it was the two small ones. And yeah, it took a little bit longer. So hopefully we've seen now the dependence on both resistance and capacitance for how long it takes to charge a capacitor and discharge it. I hope you can see that we could really carefully tune our choice of resistor and capacitor to control how long it takes to charge and discharge. And it turns out that this is how a lot of different timing circuits are created. We put different resistors and capacitors in them, and that changes how long it takes to charge or discharge. This is how we control intermittent things like your windshield wipers. Your circuit is changing, and the combination of R and C gives you different amounts of time for charge and discharge, and therefore wiper go and wiper not go. So I went back to the little resistor and the big capacitor, 51,600 ohms and 10 microfarads. That seemed to give us kind of the easiest to watch in terms of not taking too long or not happening too fast. If you're curious about the mathematical functions that describe how long it takes to charge a capacitor or what the potential is at any given time, I encourage you to look in your book. It is discussed there, and you will study this more in a later physics class. But let's just come up with a qualitative idea of potential versus time for charging and discharging. So let's go ahead and charge this, and we'll just look at whether it's going relatively fast or relatively slow at the beginning or the end. So we'll start charging. Notice it starts pretty quick. It approaches 5 volts, but doesn't get there. That sounds a lot like an asymptote to me. So I expect an asymptote at 5, and maybe some function that's got this kind of shape. Let's go ahead and discharge it. Again, we're starting at 5. So we'll disconnect the power supply, start charging it. It goes very rapidly at first and then kind of trails off at approaches 0. That also sounds like an asymptote to me. So some function that has a shape like that. So you'll study these more in a later physics class, but I just wanted you to kind of think about what functions could have that shape. Let's now look at a capacitor and a light bulb in parallel with each other and see what happens to currents through the two branches and through the main circuit as the capacitor charges. Basically, if current is going to flow, it could flow in two particular paths. It's going to pass through this light bulb, the second light bulb, and back to the power supply. But there's another route it could take as well. It could appear to flow through this capacitor. Now, current doesn't really flow through a capacitor, but electrons can get taken away from this plate, and electrons can get added to this plate. And while that is happening, while the capacitor is charging, it appears like current is passing through. So what do we expect to happen to these bulbs? Well, at first, when the capacitor is uncharged, it acts like a bare wire. So if this is a bare wire, it's shorting out bulb B. So why would any current flow through bulb B, which has resistance, when it could flow through a bare wire? So at first, B is off. How about A? Well, A is going to have a lot of current because it's basically the only thing in the circuit at first, or it appears to be. So at first we expect A to be bright. What happens as time passes? Well, this gets charged. It can't take any more electrons away from here. It can't add any more to here. So current stops being able to flow along this green path. So we lose the current due to this path. We gain the current due to the purple path because now if electricity is going to flow at all, it has to go through the bulb. So later B is on, and it gets brighter as the capacitor charges. This one, as we switch from the less resistant path to the more resistant path as the capacitor charges, it will dim. So hopefully we understand that logic, and that's the logic you want to use as you're solving these problems. What's going to happen to the roots current can take when the capacitor is uncharged at the beginning? What's going to happen when it's charged after a long time? And we just ask ourselves how that's going to affect current flowing through different branches. Let's see what this looks like in real life. Okay, so here's our circuit. We've got a wire from the power supply to this first bulb. So that's bulb A. Bulb A is connected both to the 1 farad capacitor and to bulb B. Both of those are connected back to this junction, which go back to the power supply. So as we said before, we expect bulb A to start out bright and dim. We expect bulb B to be off and then turn on as the capacitor starts to charge. So let's turn it on and see what happens. So we have bulb A is bright, appears to be getting dimmer. I'm starting to see a little bit of light coming out of bulb B. So I think that's as we expect. So again, as you're doing this, you want to talk about what's happening at the beginning as the capacitor is charging, what happens after it's been on for a long time.